Hey everyone, my name's Thatcher, and this is episode 3 of my DCTL coding tutorial series. In this episode, we're going to be going over how to make color space transforms, or IDTs, input device transforms, so that you can support new cameras in your color management pipeline. In order to do that, we're going to go through 5 different topics here. First, what is a color space? How do color space transforms work? We're going to go ahead and make a Fuji F-Log2 to DaVinci wide gamut / DaVinci intermediate input device transform. We're going to talk about some basic ways that you can verify that your IDT is correct. And finally, we're going to set up a Fuji F-Log2 to ACES IDT that works within the ACES color management and ACES transform tools within Resolve. Let's start off with what a color space actually is. Color spaces ultimately are defined by exactly 2 things. The first is going to be the transfer function. This is a function that maps between the code values that are in your file and linear light. Depending on whether it's a display or scene referred color space, the linear light could be referring to the light that comes off of the display that is intended to be reproduced by the display, or perhaps the code value could be converted to linear light referring to the light that is present in the scene that was captured. Cameras will shoot in a scene referred color space, meaning that we have a mapping between the light that was in the scene in front of the camera and the final code value that ends up in the file. So that's transfer functions. In Resolve, the transfer function is called gamma. The second half of a color space is the color primaries. This is specified by the CIE 1931 XY chromaticity coordinates for pure red, pure green, and pure blue within that color space, as well as pure white. White meaning a code value in which red, green, and blue components are equivalent. Let's take a quick look at how these 2 things are specified for Fuji F-Log2. I've got the Fuji F-Log2 datasheet open here on the right. If I scroll down, we can see the function that converts between F-Log2 and scene linear, the amount of light that was recorded from the scene in front of the camera. As well, we have the inverse of this function, the transformation from scene linear to F-Log2. If we scroll down more, we can find the F-Log2 color primaries. Here we have a table in which for red, green, and blue, as well as white in the F-Log gamut, we have the X and Y chromaticity coordinates. It turns out for this color space, these coordinates are actually equivalent to Rec 2020. So F-Log2 has the same color primaries as Rec 2020. So that's what a color space is. But given 2 color spaces, how can we convert from one to the other? That's why we have color space transforms. So how do color space transforms actually work? In order to do a color space transform, we need both a source color space and a destination color space, so we know what we're transforming between. For the source color space, we'll need the transfer function and primaries. And for the destination color space, we'll also need its transfer function and primaries. Then, given some RGB code values in the source color space, the color space transform will take 4 steps in order to convert it to RGB values that are now in the destination color space, that reproduce the same XYZ colors to your eye. Here are the 4 steps. First, we will apply the linearization transfer function from the source color space to each of the RGB values. This will result in a linear image that has the source color space's primaries. The second step is to compute a 3x3 matrix A, which is the product of 3 matrices. From right to left, the first matrix will convert from the source color space's primaries to XYZ. The second matrix will apply chromatic adaptation within the XYZ space. A lot of color spaces actually use the same white point, so typically C will actually be the identity matrix. However, for conversions to ACES, typically C will actually be important. And finally, we will convert from XYZ to the destination color space's primaries. Once we have this matrix A, we will multiply it by the linear RGB values that came out of step 1. Now we'll have linear RGB values in the destination color space's primaries. And finally, we will apply the destination's transfer function to each of these linear RGB values that came out of step 3 in order to get the properly encoded destination RGB values. So that covers the 4 steps needed to implement a color space transform. Let's suppose that we recently bought a new Fuji camera and we want to convert from Fuji F-Log2 to DaVinci wide gamut DaVinci intermediate. The first thing we'll have to do is obtain these 2 sets of data, the transfer functions and primaries of these 2 color spaces. Now, I found the Fuji F-Log2 datasheet by simply Googling Fuji F-Log2 datasheet. I was able to find the DaVinci Resolve wide gamut and DaVinci intermediate color space spec by going to blackmagicdesign.com/support and then scrolling down in the support notes section until I could find that PDF. And here it is. It's the DaVinci Resolve Wide Gamut Intermediate. So I click download here, and I've brought it into my file system so I can read the PDF. Let's go ahead and write out this IDT that will convert from Fuji F-Log2 to DaVinci Wide Gamut DaVinci Intermediate. I'm going to start off by creating a new file. I'm going to call it DCTL Tutorial 3 F-Log2 IDT. In your case, you might choose to name it something more terse, like Fuji F-Log2 to DaVinci Wide Gamut. I'm going to start off by taking the transform function from the documentation. Here it is. And I'll paste it in right here. Next, let's write out in our comments the 4 steps that we're going to take. Okay, I've written out the steps needed. We're first going to linearize our RGB value using the flog2 to linear function provided in the flog2 datasheet. We're then going to take the matrix A and then multiply it by the result of this first step. Next, we'll re-encode the result using the linear to DaVinci intermediate function provided in the Blackmagic datasheet. And finally, we're going to return this result. Let's go ahead and start coding this up. First, we're going to linearize the input image with the Fuji F-Log2 instructions. Now, I'm going to have to apply this on 3 different channels, so I think it'll make sense to break this F-Log2 to linear function into its own separate dedicated function. As before, I'm going to use device float F-Log2 to linear is going to be what I'm going to call it. I'm going to go ahead and copy all of these different constants into the top of my function. All right, now that I've copied all these constants in, let's go ahead and implement this series of steps. We're going to check if the input is greater than cut2. And we're going to use powf. And let's consider this other case that the input is less than cut2. All right, that completes the flog2 to linear function. Let's put that into our code here. We'll first initialize the value we're going to ultimately return. We're going to overwrite each of the values within out with the linearized version of that value. At this point, out contains a linear but F-log gamut image. Let's obtain the matrix A that we're going to be multiplying by these RGB values here. For computing RGB conversion matrices, I would recommend this website, brucelindblom.com. He provides all the different math that's needed to convert between RGB and XYZ given the primaries of a color space. However, this is a lot of math to write in a DCTL, and there are actually websites that have already computed all the different matrices you could want. So we're going to use one of those websites. Here's a website that can compute the matrix for us and allow us to skip all of the hard math steps. For our source color space, I'm going to specify Rec 2020, as that has the same primaries as Fuji F-Log2. For the destination, I'm going to have to specify DaVinci Wide Gamut. I can see that it's not actually listed here in this list, so I'll have to type them in myself. If we open the DaVinci Wide Gamut datasheet, we can find the red, green, blue, and white primaries. I'll go ahead and copy these in on the right side. And finally, I'm going to set the chromatic adaptation type to Bradford. In this case, the white points are actually equivalent between the two color spaces, so this won't actually do anything. And in fact, if I switch it to none, we can see that the numbers do not change. And this is our computed matrix that we're going to be using. We will also be using Bradford chromatic adaptation when we convert from flog2 to ACES. I'm going to copy this set of numbers, and we'll go back into our DCTL. I'm going to paste the numbers that we copied from that website into a comment here. Let's go ahead and store these values within a 2D array. I'll declare it with float. I'll call it color matrix, and it's going to be a 3x3 matrix. We're going to use curly braces to initialize the values. I'll paste in my values here, and I'll wrap each of these in its own set of curly braces. Throw commas at the end, as well as commas in the middle. And I'll end the whole line with a semicolon. There we go. Next up, let's multiply the RGB values that are within out by this matrix that we just wrote. It would be tempting here to write out.x is equal to this weighted sum. However, then I'll be overwriting out.x, and in my later lines, that could be problematic. So let's assign this to a new variable. I'm going to declare a float red destination, RD, is equal to that. And let's do something similar with green and blue. The way these indices work for the color matrix is that this first number here, in this case 0, corresponds to which row of the matrix we're interested in. And then the second index represents which column of that row we're trying to pull out. So you can see in this first line, we're going to take out.x, we're going to multiply it by the 0th row, 0th column of the matrix. Then we're going to add on the green, and we're going to multiply it by the 0th row, the first column. And then we're going to do the same with the blue channel, 0th row, second column. Let's save this result within out. I'll use make float 3 and save it like so. Now we must take out, which is a linear image within the DaVinci wide gamut primaries, and apply the DaVinci intermediate encoding function. I found the log curve here in the DaVinci intermediate datasheet on the right. We can see that there are 6 parameters, and then we've got 2 different functions. This forwards one converts from linear to log, and the inverse converts from log to linear. We're going to be using the linear to log function for this step. Let's go ahead and write out that function as we did with flog2 to linear. I'm going to call it linear to DaVinci intermediate with the first parameter called L, simply because that's the parameter that is used here. Let's declare all 6 constants at the top. Let's go ahead and implement the rest of the function as described here. Now we can see we have to take the log base 2. Let's check the documentation to see if we have a log base 2 function. If we scroll down to the list of supported math functions, we can see we do have a function called underscore log2f. So we'll go ahead and use that. All right, now we've completed the linear to DaVinci intermediate function. Let's apply it to each of the 3 channels within out. And finally, we'll return out. Okay, let's see if this DCTL will properly convert to DaVinci intermediate, DaVinci wide gamut. I'm going to open it up in Finder, and then I'm going to copy it over to my LUT folder. Then I'll restart Resolve because we have a new DCTL. We're back in Resolve here, and I have two clips that were shot in F-Log2. Let's open up our DCTL and see if it works. We can see that there is a difference in the image after I have applied the DCTL. This tells us that it is successfully compiled. But how can we tell whether or not it was actually correct? There are two basic tests that we can do to identify if our IDT and overall color management is doing the right thing. The first one is perhaps the easier test. The data sheet will tell us what code value corresponds to black, mid-gray, and some kind of white point. Additionally, the DaVinci intermediate sheet will also tell us what code values correspond to certain luminance values. All we have to do is make sure that these match up through the end-to-end pipeline. Let's take a look. The most obvious one here is that we have a code value corresponding to 18% mid-gray of 400 out of 1023. Let's go into Fusion, and we're going to generate this code value. I'm going to enter 400 out of 1023, and I'll send it into our DCTL. And now we have a new code value, but is this correct? Well, let's take a look at the DaVinci intermediate datasheet. We can see here in the DaVinci intermediate sheet that 18% gray should correspond to 0.336043. Going back to Fusion and putting our mouse over, we see in the bottom left corner a code value indeed of 0.33604. As a result, I believe that middle gray has been correctly mapped within our IDT. There's one other thing that we can do to make sure our overall color management and IDT are correct. However, it requires access to the camera that's shot in the color space that you're trying to implement. The first step is going to be to take the camera and shoot an exposure bracket. We'll then use our color management to convert to linear and apply the necessary gain and make sure that we can match the images from the different exposures. If we can match them, then that implies that our log to linear and linear to log functions are correct. Let's try this out with our Fuji F-Log2 footage. Here I've got our DCTL, and I'll apply it to these two clips. This clip was shot at some exposure, and this clip was shot, I believe, 3 stops brighter. We have then converted to DaVinci Intermediate. Let's apply a color space transform to convert from DaVinci Intermediate to linear. We'll use no tone mapping, this is critical. And we'll use the same CST over here on the right side. Notice that neither of these CSTs have tone mapping or OOTFs checked. Next up, we'll apply an amount of gain. I'm going to pull up the color gain tool. In order to match the brighter exposure to the 3-stop darker exposure, I'm going to have to apply a gain of 1/2 to the third. So that is going to be 1/8. I'll apply a gain of 0.125. Next, I'll apply another color space transform to bring it into Rec. 709 so that it's easier to look at this image. I'll go from DaVinci Wide Gamut Linear to Rec. 709 Gamut 2.4. I'm going to use the OOTF. And now the moment of truth. We have the color space transform on the left side that was exposed 3 stops brighter, as well as the one on the right side. Let's see if they match. We can see on the waveform that there's hardly any movement at all. It is merely that the image on the right is noisier than the one on the left. Upon visual inspection, we can see that they are indeed pretty close. I do see a slight shift in the reds, but I don't think it's anything serious. As a result, I have reason to believe that our F-Log2 to DaVinci Intermediate transform is probably correct. If I was not able to match the exposure of all these images in this exposure bracket that I took, then that would imply that my IDT or perhaps my overall color management is incorrect. In that scenario, one option would be to see if you got the input color space wrong, or perhaps if there's some kind of error or typo within this DCTL. Some cameras also don't correctly implement the reference log curve. So that could be another way where you could go wrong. Now that we have a transform from Fuji F-Log2 to DaVinci Wide Gamut and DaVinci Intermediate, let's make an IDT that works with ACES. This is one of the more interesting features with the DCTL language. I'm going to copy and paste this DCTL, and I'm going to rename it to F-Log2 ACES IDT. And before we make any modifications, let's take another look at the How Do CSTs Work slide that I have. As you recall, we need both the source color space and the destination color space's transfer functions in primaries. We've already been playing with the source color space's transfer function in primaries, but now we need the same for ACES. ACES IDTs will all have the same destination color space. The transfer function will be linear, and the primaries will be the ACES AP0 primaries. For the ACES AP0 primaries, I typically refer to Wikipedia. If we scroll down here, then we can see the ACES AP0 red, green, blue, and white point primaries all indicated. Okay, so now we know the ACES primaries and the transfer function being linear. Let's start modifying our code. I've pulled back up our ACES IDT. We're not going to need the linear to DaVinci intermediate transform. And you know what? Let's change our pseudocode comments. Instead of applying the linear to DaVinci intermediate function, we'll simply keep the linear values that we had before. That allows us to just delete these 3 lines. Our matrix now, however, is incorrect. This matrix converts from the Fuji F-Log gamut to the DaVinci wide gamut, whereas we actually want it to convert to ACES AP0. Let's go back to our color space calculator tool from before. Instead of going from Rec 2020 primaries to our custom DaVinci wide gamut primaries, we'll instead select ACES AP0. In this case, it is critical that we choose the Bradford chromatic adaptation. If we were to choose no chromatic adaptation, we would get different numbers, and our white point would not be preserved over the course of our entire pipeline. I'll go ahead and take this matrix and paste it back into my DCTL. Let's fix the formatting. And we've got the new matrix. I should probably indicate here in a comment the primaries that this matrix transforms between. And we'll do something similar on our previous DCTL. All right, now we've written the transform that goes from Fuji F-Log2 to ACES AP0 linear, which is the color space that ACES transforms expect. There is one more step that we should do in order to make this work with ACES color management within Resolve. Let's pull up the documentation, and we can see that in section 4, we have the content related to ACES DCTLs. We have just created what is called a non-parametric transform. We'll scroll down to the writing a non-parametric ACES transform, and essentially all we have to do is add this line to the top of the file. As described, we did convert from the image source color space to the AP0 linear color space, so we're doing the right thing. Next up, instead of saving this DCTL in our LUTs folder, we actually have to save it to a different location. Something that's kind of funny is that within the documentation, they've listed the folders that we should save our ACES IDTs into. However, someone's clearly left a note here that they have to double check these folders again for a future reference. As a result, I've already found which folders we have to save this in for macOS and on Windows. On Windows, you're going to go into your home directory and then into this hidden folder called App Data, and then you can find the rest of this path that ends with ACES transforms. And on macOS, it's similar. You're going to go into your home directory and then into this hidden folder called Library. And from there, you can find this ACES transform folder as specified on screen. I've pulled up this folder on the top left, the ACES transform folder. And on the inside, you should see this IDT and ODT folder. If they don't exist, you might have to make them yourself with these 2 exact names. Let's take our new ACES IDT for F-Log2, and I'm going to go ahead and copy it into my IDT folder. You can see I already have a few others in here. Similarly, if you had made an ACES AP0 linear to, say, Fuji F-Log2, you would actually put that in the ODT folder. Now, we'll go ahead and restart Resolve. And hopefully when we restart it up, we'll see the new IDT within the ACES transform plugin. All right, we're back in Resolve. Let's take this clip over here and see if we can find our new ACES IDT. I'll pull up the ACES Transform plugin. If we scroll down here, we can find our DCTL Tutorial 3 Flog2 to ACES IDT. I'll go ahead and select that, and we can see that it indeed has transformed the image. I would also like to point out that if we go into our project settings and go to color management, if we set the project over to ACES, say ACES CCT, we can set the input transform to be this new DCTL that we made. This enables us to use our own custom IDTs as a first-class citizen within DaVinci Resolve Color Management, provided that we're using ACES Color Management. And there we have it. That concludes today's tutorial on color space transforms and writing your own IDTs within Resolve. In summary, we discussed what a color space is, which is a transfer function and a set of primaries. We discussed the 4 steps needed in a color space transform. We made an IDT that goes from Fuji Flog2 to DaVinci Wide Gamut DaVinci Intermediate. We showed how to prove that your transfer function implementations were correct within the IDT. And finally, we showed how to make a new IDT for ACES transforms and ACES color management within Resolve. Unfortunately, it's not possible to make the IDT show up within the Resolve color space transform tool, but you can still use these IDTs from the LUT browser and within the DCTL tool. That's all I've got today, and I hope to see you guys in the next episode of this DCTL coding tutorial series.